This webcast is looking at Worksheet 8E on quantitative energy conservation, and it's just going to do the first, I believe, 7 problems that show how to apply those equations to calculate different types of mechanical energy. Okay, so in the first one here, we have the scenario of a physics binder sitting on a classroom table. And the purpose of this problem number 1 is to just talk about how important it is to understand our reference for zero gravitational potential energy, which generally we take to be the floor or the ground where we are. Okay, so we have, the first scenario of the physics binder. Here's the table. The physics binder is sitting on the table, and it says that the zero reference point is chosen to be the table itself, and it's sitting on the table, so the height of the book and the reference point for zero gravitational potential energy is the same. So therefore the gravitational potential energy of this binder is going to be its weight, which is its mass times 9.8, times the height, but here the height is 0 meters because it's on the table and the table is our zero reference point. Therefore here we would say that the gravitational potential energy is 0 joules. What if we had the same situation, right? The same table, the same binder, but now the floor is where we say our zero reference point is. So when something's on the floor, it's at a height of 0 meters. Well, now it's on the table. The table is 0.68 meters above the floor. So the binder's gravitational potential energy would be its weight, which is the 3 kilograms times the 9.8 newtons per kilogram, times its height, which is 0.68 meters. And let's see what that is. We get 19.992 joules. Okay. What if we have the same table with the same book, but now we're saying the ceiling is where zero reference point is, and this book is actually 2.5 meters below the ceiling. So it's like you dug a hole in the ground. It's below our zero reference point. So here the gravitational potential energy would be its weight, which is 3 times 9.8, times its height, which would be negative 2.5 meters. And we get negative 73.5 joules. So it is possible for gravitational potential energy to be negative. We don't often see that. Typically, we would say that on the floor or on the ground around us, that is where the gravitational potential energy is 0. But that is somewhat an arbitrary choice, as this example just showed. Okay, here in number 2, we're talking about what is the change in gravitational energy of a squirrel that comes down. It's originally on top of a 50-meter high tree, and then at the end it's only 2 meters above the ground. So we're looking for the change in the gravitational potential energy, which is the squirrel's weight times the final height minus the initial height. Okay, so the squirrel's weight is the 3 kilograms times 9.8 newtons per kilogram. The final height is 2 meters, but its original height was 50. Okay. So we get negative 1,411.2 joules. The gravitational potential energy got smaller by that much because the squirrel came down to a lower height. Okay, Let's look at 3. How much kinetic energy does this SUV have when it's traveling at 70 miles per hour? Well, one thing I notice is that miles per hour, that is definitely not a standard unit, and so I better convert that. So 70 miles per hour, let's remember how to do this. 1 mile is 1,600 meters, and 1 hour is 3,600 seconds. And so I can convert this into meters per second, and I get 31.11 meters per second. Okay, so now I'm ready to find the kinetic energy, which is half of the SUV's mass times its velocity squared. So we have a mass of 2,000 kilograms, and its velocity is 31.11 meters per second. I have to square that. And so it has a lot of kinetic energy. It's 967,832.1 joules. Okay, let's look at number 4. How fast does this 50-gram arrow have to travel if it's going to have 40 joules of kinetic energy? Well, one thing I'm noticing is it's giving me the mass in grams, which is not a standard unit. Let me go ahead and just convert that before we do anything. So 50 grams, and I know that it takes 1,000 grams to make 1 kilogram. So that's 0.05 kilograms. Okay, so it's talking about kinetic energy, and the formula for that is that kinetic energy is 1/2 the mass times the velocity squared. So here I'm going to be I'm solving for V. That would tell me how fast this arrow has to be going. So I'm just going to move my equation around. The velocity would be 2 times the kinetic energy divided by the mass, and I'm going to have to take the square root of that, right, to solve for just V. And so I get 2 times the 40 joules divided by the 0.05 kilograms. And I get 40 meters per second. Okay, let's look at number 5. What is the change in kinetic energy of a 14 megagram truck that slows from 28 meters per second to 8 meters per second? So I have a unit here that is not in a standard unit. My standard unit for mass is a kilogram, not a megagram. So I need to convert that. 14 megagrams, I know that 1 megagram is 10 to the 6 grams, but what I really need is kilograms. 1 kilogram is 10 to the 3rd grams. So see how my megagrams cancel, my grams cancel, and I'm going to be left with 14 times 10 to the 3rd kilograms. Okay, so let's see, it's looking for the change in the kinetic energy, and so I need to use the right formula for that. The change in kinetic energy is half of the mass times the final velocity squared minus the initial velocity squared. And so that's going to be half of that 14,000 kilograms. It was originally going at 28 meters per second. It ended up going at 8 meters per second. So I've got 8 squared minus 28 squared. Notice that I'm squaring the final velocity and then subtracting the square of the initial velocity. I'm not taking the difference between them and squaring that difference. Okay, so 0.5 times 14 e to the third times 8 squared minus 28 squared. And I get negative, let's see, I'm going to have to write it out to say it. I've got negative 5,040,000 joules. Okay, let's see here. And let's do one of the elastic potential energy ones. Here's number 6. A bungee cord, that's elastic, right? It stretches and then it goes back to its original shape. It stretches 25 meters. So that 25 meters is the displacement of the end of the bungee cord. It has a spring constant, that's like a K, right, of 140 newtons per meter. And it says how much energy is stored in the bungee cord when it's stretched that far. Well, it's storing elastic potential energy, which is half of the spring constant times the displacement squared. Everything here, thankfully, was in standard units, so I don't have to convert anything. And let's find out what this is. It's 43,750 joules. And then finally, let's look at number 7. How much energy is stored when a railroad car spring is compressed 10 centimeters? Okay, so that is, centimeters is not a standard unit. Right away, I'm just going to convert that. This is the delta X. It's 10 centimeters. There are 100 centimeters in every meter, so that's 0.1 meters. And it says the spring requires about 10,000 newtons to be compressed by 3 centimeters. Well, remember Hooke's law says that the applied force equals the spring constant times the displacement. And I really need to find the spring constant. So that would be the applied force divided by the displacement, which would be 10,000 newtons. And I need to make that 3 centimeters into a standard unit, which would be 0.03 meters. And so this is 333,333 newtons per meter. Okay. And so it's asking me, the real question here is how much energy is stored. So it's going to be stored as elastic potential energy. That's half of the spring constant times the displacement squared. That's going to be half of the 333 newtons per meter times 0.1 meters squared. And I get 1,666.7 joules. Okay.